So here is another lecture in Fundamental of Computer Vision, which we will talk today about the epipolar geometry. What is that? We need again to map a certain particular point in this image plane, for instance, to another point in this other image plane. We need to do that. But we need to do this a little bit differently than what we did before, in a sense that when we do these maps, can we do like the maps with point to point, or where is exactly that point? In another sense, if I'm giving you this point here, where is this point is exactly in that particular place? Or if you were to think about this point, or this point, or this point, or this point, if you see this here, how you will be able to see this in this image plane? How you will do that? So let's go through like some important steps and definitions, and bear with me until we prove at the end what we are exactly getting. So now we have this image plane. The point P is just like in the 3D object. Now I have the center of projection of this particular camera and the center of projection of another camera. Then if you connect this center of projections of these cameras together, this is something called baseline. Remember that. This is called baseline. This baseline will intersect the image plane of the first one in something called E dash, and it will interface the other one in something called E, and this is called the epipole, which is the projection of these over the image plane. This is called the epipole. This guy, which consists of the 3D object connected by the two center of projections of my camera, this plane is called the epipolar plane. All of these expressions is very important. This guy and this guy is called the epipolar line. What is this epipolar line? It is just the intersection between this plane and that image plane and that image plane. If you do this intersection in the 3D, you will see that the intersection happened on this line and the intersection happened on this particular line. Can you see that? This is called epipolar line. So again, just to review, what is this? Epipolar plane. What is this? Epipolar line. What is this? Epipole. All of this you need to be aware of. What is that? Baseline. So in another sense, there is a potential matches for X which lies on the epipolar line of L dash. What does that mean? Any point in that particular line, either this, or this, or this, or this, will end up projected in just one point in my image plane. Correct? But how this will be projected in this other image plane with the other camera? Oh, so this is, if we were to project this to the image plane according to this line to the center of projection, it will end up at this point. If I do this, it will end up at this point. If I do this, it will end up at this point. If I do that, it will end up at this point. Oh, so this point mapping to all of these points, which is in the epipolar line. Why is that useful? So you showed us right now geometrically that this point in this image plane, if you were to try to search in where is this in this image, I'm telling you a certain particular constraint that it lies only in this particular line, which is called epipolar line. Why is this useful? This is useful now because your search algorithm will search only through one line instead of searching for this point in the whole image. So instead of saying that, oh, where is X? If this is X, 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 and so on and so forth, you are just searching in this particular line. So search-wise, a lot less computationally. Correct? And this is, by the way, it is the same the other way around. If I were to tell you, like, okay, what is this point in this image plane? It's exactly the same way. If you do this, and then you take these points is here, and then take these points here, and then this take this, all of these again will lie on the epipolar line of the other image. So now we can match or map a point to a line. So if I know this point there, it will lie on the other particular place in the other image, which is called the epipolar line. So just like again to show you these things, here I have the x. X can map to anything in this particular line, which is the epipolar line, and this p is matched to x dash, p to x other dash, p to the x other dash, and so on and so forth. So at the end, this point will map to any other one here, but not only this point red will map to any one in this epipolar line. One important other things that this epipole point will be the point that all of the epipolar lines will intersect in. So if you have any other epipolar line, all of them will intersect at this particular E in this image. If you go to the other image, all of the epipolar line will intersect at this particular point also, epipole, which is the intersection of the plane with again the two image planes of the two cameras. As you can see from here, even if like differently, this epipolar line, all will match at a certain particular point. So if I'm giving you this image and I'm telling you that this is the two images and these are the epipolar line, meaning that this is the epipolar line, this is another epipolar line, this is another epipolar line, and so on and so forth. And as you can see from here, this point will map to any points inside that particular epipolar line. And if you do the search, you will find that this is mapped to exactly this. The same exact one here, this will map to anyone that is in this epipolar line. And then if you do this search, you find this, and so on and so forth, as we will see shortly. But you are just searching one line with all of these examples. So I'm giving you that these are the epipolar lines, and I'm asking you, where is the epipole? You just told us that the epipole will intersect at a certain particular point if you give me like a couple of these epipolar lines, because all of the epipolar lines will intersect at a certain particular point. But here they are not intersecting. Where is that? Basically, I told you that they have to intersect, but I didn't tell you about the size of this image. If your image is small, as an example here, you will not see this epipolar line. Correct? It will intersect, but a little bit further away if your like CCD is even bigger, if your image plane is even bigger. And here is exactly the same things. If you do that, it will intersect at a certain particular point, but if your image plane is bigger. Correct? So at the end, they have to intersect in a certain particular point. Here is where is the epipole. This is, if you can look closely, this camera or image plane, it's like a certain angles together, correct? What will happen if this, instead of having like that, with this angle, it is like this, flat? They are like parallel to each other. The camera 1 and the camera 2, the image plane of this camera 1 and camera 2 are parallel to each other. How do you think the epipole will land in? First of all, when you have like this, like parallel like that, all of the epipolar line will be parallel. So if the epipolar line will be parallel, there is no intersection, yes? Or you can think of that mathematically intersecting in the infinity. Yes, so the epipole will be in the infinity, and that's what we are expecting, the epipole at infinity. So it's like this, epipole, bigger, 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 until it begins to be infinity. So just like to remind you again, what we are mentioning is epipolar constraint. What is that? I'm trying to match a point in the left image to a point in the right image, given a certain particular constraint, that this will land to any points in this particular place or this particular line. This is what we are trying to say, that we have now an epipolar constraint, that this point X will land to that particular epipolar line. It won't land here, it won't land here, never. But it has to be something in this line. Okay, so epipolar constraint now reduces the search to a single line, as we mentioned. So this guy on the left will be just like in the one particular line in the image to the right. But how we can compute the epipolar line then? You just told us that there is an epipolar constraint, which will be just one line. How we will be able to calculate that line? This is what we called, or what we will use to do that, something called essential matrix. With this essential matrix, you will match X to a certain particular epipolar line. So like this X need to be in that particular lines in the other image plane. So this means that in order to map a point to a line L dash, I have to multiply it by something. And if I multiply this by that something, I will end up in this particular line, correct? So what I'm saying, like E multiplied by X is equal to L dash. Another thing, given a point in one image, multiplying but what we call the essential matrix will tell us the epipolar line in the second view. And what we are targeting is how to get this E. I know that this should be something. There should be something that maps this X to that particular L dash. So I will assume that it is multiplied by a certain particular matrix or a certain particular value here, which is called E. And this is we call the essential matrix. So what we know about the essential matrix, it is a 3 by 3 matrix that will encode this epipolar geometry. Just to remember, what I have told you so far before the previous slide, all in geometry. But we need to translate that to algebraic equations. We need to see the algebra. We need to see this. We understand visually that this will lie in that. But how we can do this with the equations? This is what we are targeting right now. So the essential matrix is 3 by 3, which matrix that encodes the epipolar geometry. And in another sense, I will give you a point in one image. I will tell you exactly what is the epipolar line in the second view. Just before moving forward, just to recall with the idea of vector or cross product and the dot product. If you were to have two vectors like that, the cross product will be like a vector that is perpendicular to both of these. How about if I'm telling you dot product between C and B? Dot product between any vectors that are perpendicular to each other will give you 0. What is this product? Dot product B multiplied by A is equal to 0, and so on and so forth. So the dot product between two vectors perpendicular to each other will give me 0. The cross product, if I cross product two vectors that is in one plane, will give me another vector that's perpendicular to this one, to this particular plane. If I cross product a vector with itself, it will give me 0. And I told you earlier, because the cross product will end up by sine theta, magnitudes A and B multiplied by sine theta, but the cross product will be A and dot multiplied by B but cosine theta. And if theta is 90, the dot product will give me 0. But if theta is 0, then the cross product, the dot product, the previous one, the dot product will give me 0. But then if the theta is 0, sine 0 is 0, so the cross product will give me 0. And I showed you like how to do the multiplication in a matrix form, that A cross product with B. I showed you earlier how to get this matrix. But also this can be written in that form, that A cross product B will have a certain particular skew matrix multiplied by B. You can think of this again as I, J, K. At the very beginning, you just put I0, the second will be J0, the third will be K0, and so on and so forth. And this is, as you can see from this matrix, it is skewed symmetric. So the A1 will be minus A1, the A3 will be minus A3, and so on and so forth. So now I can write the A cross product B as this. It will be a matrix AX multiplied by B, correct? Just remember that because we will need that. Okay, sounds good. Geometrically speaking, if I have a line L with this equation, how I can write this in a vector form? This is A multiplied by X plus B multiplied by Y plus C is equal to 0. So this means that I can write L as an A and B and C as a vector like that. correct? If I'm asking you, if you have a point X which lies in a epipolar line L, what will be the results of X transpose L? The vector of a point, the X transpose, or the vector of that point, it will be like a vector in the same exact direction at this point, yes? So it will be like something like this vector, correct? The vector that will actually carry the L, it will be something perpendicular to that particular plane. If you do this two dot product, it will give you 0. So X transpose L will give you 0. So now we know that X transpose L is equal to 0, but also we know that E of X is equal to L dash, if you recall. I told you that you have a point X. We need to map this point X to L dash, so I have to multiply it by a certain particular matrix, which you call the essential matrix. If you plug this here, you will end up with this. Why? Because X transpose L is equal to 0, but also X dash transpose L dash will be equal to 0, correct? The same things. You can apply this to the right or to the left. It is the same things. So X transpose T, it is here. L dash, it is EX. So it is here. So X dash transpose multiplied by EX will be equal to, we know, 0. Correct? Then, what is the difference between the essential matrix and the homography? I just reviewed the homography, yes? What is the difference conceptually between the essential matrix and the homography? Earlier, I'm giving you like this matching point, and I'm asking you to get the H, correct? If you recall, I just like remind you about this. This points in the image dash, and this points in the image like plane X, and I'm asking you like get the H. I will give you 4 points. I will give you 4 points matches, and then you will apply this. You get the 8 equations. You will be able to solve the 8 equation. You got the H. But with this one, I'm not mapping a point to a point. I'm mapping a point to a line. Correct? I'm mapping a point to the line. So the essential matrix maps a point to a line, because here is the line, this is the point, this is the intersection, or this is the relationship with this particular matrix E. But where basically the essential matrix come from? Okay, so just to recall, if we were to map a point to another point, if we were to say like, hey, this is the X dash and this is the X, how I can get the X to the X dash? Or in another sense, how I can map this X to the new coordinate O dash? Do you remember when we did this earlier? We just do the translation and then the rotation. Yes, if you do this translation from that left to the right, and then you do the rotation, this is exactly the same things as we did earlier. So X dash will be the X after translation, and then multiply by the rotation, then you will get to the X dash. Okay, so sounds good. This looks familiar to things that we did earlier, correct? When we moved from the 3D object to the 2D central projection camera. We move the point from this by C, if you recall, and then we do the R. So the camera to camera transform, just like world to camera transform as well. But if you look at these 3 vectors, T, X, and X dash, T, X, and X dash, they are coplanar. What does it mean, a coplanar? Meaning that all of these vectors are in the same plane. If they are in the same plane, they're called coplanar. Or if they are in a plane that is parallel to a certain single plane. So 2 of them are here and the third are like parallel to that plane. Or 1 is here and the 2 others are also parallel to that particular plane. All of this can be called coplanar. But why is this useful? Why this information is useful? You will understand that in a minute. If I were to cross product T multiplied by X, and then the results will be multiplied by X transpose, what this should be equal to? Let's go step by step according to what we know about the cross and dot product. T multiplied by X, T cross product with X will end up with what? With a vector that is perpendicular to that particular plane. Correct? And if I do that dot product with the X, with this vector, what will be the results? It is perpendicular to any vector like in that plane, correct? So the results will be equal to 0, correct? That's why like coplanar now, we get like a useful stuff from that. So the results will be 0. So what about not that vector? If this vector is transferred like to another place here or there or there, so X minus T or X, whatever, like you just like transfer it, will give you what? X minus T transpose is still equal to 0, yes, because it's still in the same plane and the other one is just perpendicular. So all of this will be equal to 0. Also, the transformation with this is equal to that with the coplanarity. With the rigid motion is equal to this. Try to play a little bit again with the math. Just remember, what we are targeting is what? We need to get what is E. What is the matrix, essential matrix E? This is what we are targeting. So please, I don't want to lose you while we are going deep to the math. This is just steps to show you what we are targeting. We need to get to the E. So we already proved that with the rigid motion, X dash will equal to this. With the coplanarity, this is true. Okay. So I know from here, X minus T, X minus T. So X minus T from here is what? Multiply from the right, R minus 1. This is orthogonal, so it will be R transpose. X dash will be R transpose R X minus T, correct? What I did is just multiply this by R transpose from the left, or R minus 1. But this since it is orthogonal, so R minus 1 is the same as R transpose. Okay, so if I do this, this is equal to I. So X minus T is equal to this. But I need X minus T transpose, so I need this transpose, so I need this transpose. How I can do that? This transpose is equal to X dash transpose R transpose transpose, which is R. So now, no, we know that this is equal to this, which is here. And this is here. Are you following me? Just very simple math. Okay, what's next? We already knew, or we already said that T cross product with X can be written in a two multiplication of the multiplication of two matrices. Yes, if you remember, like the A cross B, I told you that we can call it AX. T multiplied by B, cross product by B, it can be also a matrix T multiplied by X, as I showed you earlier. Okay, nothing new. And then just take this R with this T, put them in a certain particular parenthesis, and then X dash transpose will be equal, X dash transpose will be multiplied by something multiplied by X is still equal to 0. This is what I will call the E matrix. So this is the essential matrix, which is this particular thing. So now I have the essential matrix that X dash transpose EX is equal to 0. Okay. But also we know from the epipolar line that X transpose L is equal to 0, X dash transpose L dash is equal to 0, and then we know also these particular things. But how about if we multiply the epipoles with the matrix, essential matrix E? So if I were to ask you how I can map the epipole from one to the other. So earlier we said that E multiplied by X will give me the L dash, yes? So I'm mapping the X to the L dash. But if I remove this X, so the mapping the X to the L dash, if I remove this X and instead of the X, I just put the small e, the epipole, what do you expect that will be? Now I am not mapping a point to a line. Yes? What will be the results? Because all of these intersect at just one point. All of the epipolar lines are just one point, correct? So just like the matrix E, essential matrix multiplied by E, is just not but 0. Okay, so this is points in normalized coordinates. Now I have assumed that I have two calibrated cameras, which I know the origin of the left and I know the origin of the light, and it is calibrated. I know what is this related to that. In order to go from here to there, I have to translate and then rotate, or I have to do these multiplications and so on and so forth. And E multiplied by X is equal to L dash, and this point aligned to a camera coordinates axis, which is called calibrated camera. We know all of these things. But how we can generalize something like that to be in uncalibrated cameras? So calibrated cameras is something like a little bit constrained, but if I have something very, very general, this is what we will learn next, the fundamental matrix. So the fundamental matrix is a generalization of the essential matrix, where the assumption of calibrated cameras is no longer valid. I'm not accounting that both of them will be calibrated. Both of them actually are not calibrated. And this is what we will do like in the next slides.